well. Okay, so we'll move on, and we'll get to hear now from the final grant of the series, which was the complex oral health products, characterization, modelling and manufacturing challenges. So hopefully Panagiota is here, and she'll be talking to us, and it'll be very interesting to hear about your recent developments to the manufacture of complex fluid formulations. So hopefully, Panagiota, you'll be able to share your screen.
Yeah, okay, I'll try that now. Let me see. Here I am. Share. Is that happening?
Not at the minute, so.
Okay. So if I do that, okay.
Yeah, brilliant.
Should be better. Okay, great.
Fantastic.
That's fine. Well, thank you very much. So what we are going to do this afternoon in our talk is to present some recent developments from Coral on the viscoelastic effects during processing of complex fluids. So the talk will be delivered by myself, just to give you an introduction, and then by two of our researchers, Tom and Giovanni. Before I continue, I thought it was a good opportunity today to wish a happy International Women in Engineering Day to all our female researchers and the participants. So I will try to see if I can, I cannot change the slides. Maybe I'll try in this way. Okay, so our grant was one of those funded under the Future Formulations call, and it was on complex oral health products, characterization, manufacturing, and modeling challenges. It is a 4.5-year project with over a 2 million budget, and it had support from GSK, XR, and CPI. It is a multidisciplinary project with colleagues from chemical engineering, myself and Dr. Mazzei, mechanical engineering, Professors Balabani and Tivari, and Professor Wilson from mathematics. So the aim of this project was to gain fundamental understanding and to develop the methodologies that will help us manufacture complex formulations, with particular emphasis on particle suspensions in Newtonian and non-Newtonian fluids. And we wanted to follow the multidisciplinary and multi-scale approach that involved mathematical modeling, the numerical CFT analysis, and advanced experiments. And the objectives were mainly two. One was to study the rheology, the complex rheology of these suspensions, but also to link it to any microscale interactions, and also to develop the modeling and the experimental tools that would help us to understand the effect of process conditions on the suspension rheology. So the work, I'll just reveal, sorry, it takes a bit of time, all the slides. The work started from the characterization of these complex suspensions, and in previous talks and as well as in papers, we have presented the effects on rheology of having, for example, different particle types and different background fluids. We were focusing a lot on non-Newtonian, on non-aqueous formulations. And you can see here some results from this work on, for example, the effect of the particle morphology. We have, for example, here glass spheres that are perfectly spherical and non-so-spherical abrasive silica particles. And what we can see is that also the background medium affects the rheology. For example, in glycerol, the glass spheres remain almost Newtonian until quite high volume fractions, while in the abrasive particles start exhibiting some non-Newtonian shear thinning behavior. While when we are in mineral oils, actually both types of particles can show shear thinning behavior quite early on from low volume fractions. So as I mentioned, some of this work has been published already. There is a continuation of the work now of these suspensions in non-Newtonian viscoelastic media. And it is where our collaboration, in collaboration with the mathematics department, we try to develop the constitutive equations to characterize these mixtures. A lot of these background non-Newtonian fluids, sorry for that, it will all come up in a minute, are gels, and a very important part in the formation of these gels is the kinetics, how fast the gelation happens. So part of, again, of our studies on characterization of properties of these complex mixtures was to understand the kinetics of gelations. And what I show you here is, again, some work published previously on the gelation kinetics, where we tried to investigate the effects of the solvents on this gelation speed, and also on the temperature. And what we managed to develop is these maps of gelation kinetics that give us the time it takes for the gels to form, which is very important if we want to process them. So I will now pass on the talk to my co-speakers. Towards the end of the project, at the later stages of the project, we tried to understand what was the effect of the processing on these complex mixtures. And Tom will talk about the instabilities induced in Taylor-Couette systems. And Giovanni will talk about the, again, strange behaviors of solid suspensions in viscoelastic media and in stirred vessels. So it's over to you, Tom, now.
Okay, thank you, Yota. I hope you guys can hear me. So let me start sharing my screen now. Yes. And share. Okay, and switch to presenters mode. All right, so yeah, so this part of the talk is about indeed elasticity and particle-induced flow instabilities and transitions in macro-scale flows, and we are dealing this time with a Taylor-Couette flow. So Taylor-Couette flow is the flow that develops between two cylinders, either one of which is rotating. It's interesting for both reasons that it has fundamental insights into the fluid mechanics of the flow, really. It's related to the rheometer configuration. It has easily accessible theoretical and numerical predictions, but also it has an impact on mixing, and it's useful as a study in terms of mixing, and so we'll talk about that later on. So in this set of experiments, we're interested about the case of an inner cylinder rotating and the outer cylinder being fixed, and in the gap you can have a whole lot of different instabilities developing, and this is what we'll be focusing on. So we are mainly concerned about complex fluid features that we will distinguish between three properties: viscoelasticity, shear thinning, and the presence or absence of solid particles suspended in the flow. So viscoelastic Taylor-Couette flows have been widely studied in the literature, actually. There's a whole lot of different instabilities associated to viscoelasticity. Now, shear thinning, on the other hand, is a bit more recent of an advance. There's been a few papers within the Coral project on this, and what is still missing is a proper study of the competition and the interactions between both shear thinning and viscoelastic effects at the microscale in a Taylor-Couette setup. And in terms of particle suspensions, which is actually the primary focus of this project, there's been recent studies on particles suspended to non-colloidal suspensions of dilute to concentrated particles in Newtonian solvents. Our goal would be to bring all three parameters together and study the effect of particles being suspended in complex solvents with both properties. So this is what we'll be doing, quantifying elasticity of the fluid through basically an elastic time scale, and shear thinning using Corot model. Now, I was mentioning the Taylor-Couette experiment. What we will be doing in terms of experiment is actually follow the transitions in the gap thanks to a very simple visualization method. So the idea is that you take reflective flakes, non-isotropic flakes that you put in the gap, and those flakes tend to align with the flow. So if you start rotating the inner cylinder very slowly, you have a purely azimuthal flow that develops in the gap, and all the flakes are aligned in the azimuthal direction. Now, if you keep increasing the rotation speed, thus increasing the Reynolds number, the inertia of your flow, you may have some instabilities developing upon inertia or upon elasticity. And the flakes will align with the secondary flows that are caused by those instabilities. And you will see stripe-like structures, for example. And this allows you to detect the onset of such instabilities as a function of the Reynolds number or any other parameter that you can associate with the inner cylinder rotation speed. So taking a line along the main direction of the cylinder and plotting that as a function of the Reynolds number, for example, you are able to build flow maps of your flow states that show you the transition between Couette flows, typical Taylor vortex flow, the usual first instability that develops in Newtonian fluids, or other types of flows. And if you take the Fourier transform of this one, you end up with what we call a frequency space diagram or frequency Reynolds diagram, which helps you visualize the temporal frequencies of your flows and to detect other types of flow states. Now, we apply that to fluids with various complex properties, as I told you, and we will apply that specifically first to polymer solutions of different nature, so that could be xanthan gum solutions or polyacrylamide solutions at different molecular weights and in different solvents, glycerol water mixture typically, and at different concentrations. Doing this, changing all these parameters, allows us to wander through a shear thinning elasticity parameter space and sort of not really disentangle, but at least vary kind of separately the effect of shear thinning and elasticity and study these effects on our flow. And what we end up with as a main result is two very different behaviors. The first one, when you have high elastic numbers and low to high shear thinning, but you're remaining on this upper part of the graph, has to do with elastic or elasto-inertial instabilities, and I'll show you that later on. But quite surprisingly, even at seemingly high elastic numbers, if you have shear thinning strong enough, you end up with what we can call a Newtonian-like transition pattern. So typically something that you would observe in a Newtonian fluid, transition from Couette flow, so the purely azimuthal one, to the Taylor vortex instability, and to wavy Taylor vortex instability, basically Taylor vortices oscillating upwards and downwards. And this is quite surprising because you have high elastic numbers. You would expect elastic instabilities and you don't see them. And this is because of shear thinning. So it's Newtonian-like. It doesn't mean that it's Newtonian. You still see a destabilization of the flow because of the complex fluid, of the complex behaviors. And you also have a modification of the nature of the instabilities, and specifically the wavy instability. Now, this is the Newtonian-like behavior. I told you about the elastic one, the elasto-inertial one. This is what you typically get when you have, even for high shear thinning, if you have a sufficiently high elastic number, you may get a much more complex pattern of transitions, and ultimately a flow state that's seemingly very chaotic, that looks like turbulence in a way that you have a broad range of time and space frequencies, but that still happens at quite low Reynolds number, at least much lower than those you would expect for purely inertial turbulence. So this is why we label this elasto-inertial turbulence. It's a chaotic state that's caused by both elasticity and shear thinning, and elasticity and inertia. And so this, if you compare that one to that type of state, this implies much better mixing because of the chaotic state. So this is just for a solvent alone. Now what happens when you put particles in all of this? And so this is an example of a fluid that has negligible shear thinning, but still significant elasticity. On the left-hand side, you have no particles in there, and so you see transitions to the state that we call elasto-inertial turbulence. And on the right-hand side, we add 10% of spheres, very simple particles in that, so dilute system still, and you already see an effect on the transition, the primary transition, particles delaying some of the transitions and modifying the frequencies of the elastic behaviors. So you could do that without shear thinning, with shear thinning. So that's another fluid where you can see that the presence of particles on the right-hand side modifies the transitions and the flow state. So to summarize all of this, we may have complex features associated to complex fluids, but some of these features, namely shear, thinning, elasticity, or particles, may interact with each other and may have competing effects. And this is likely to have consequences on mixing, because obviously, the more chaotic your flow state is, the more efficient you're expecting it to be in terms of mixing properties. So now we are looking forward to investigating the exact mechanisms of this composition, how, like, sort of quantify the mixing that it yields, and pushing the study, this would have been done without COVID, obviously, towards more dense suspensions to bring to link it with our rheological studies in the project. And another interesting feature to observe would be the effects of particle migrations caused by inertia and elasticity, and this is what Giovanni is going to talk to you about. All right, so let me stop sharing now.
So I'm Giovanni. As Professor Angeli introduced, this part of the presentation is more about, let's say, the manufacturing challenges correlated to the mixing of solids in non-Newtonian liquids. I think most of you know that the mixing of solids in non-Newtonian liquids is pretty common in industry. When you try to mix really high solid load, or when the fluid is highly viscous or non-Newtonian, you can incur in all sorts of problems and complexities. From long mixing times, we can lead to energy waste, to reduced mixing quality with the formation of caverns or the clustering of the solid phase. So this study is an experimental study in which we employ optical technique, in particular PIV, particle image velocimeter, and particle tracking velocimetry, to investigate the behavior of solid particle stirred in a complex flow like the one produced in a stirred vessel. So the first part will be about the rheological characterization of the liquid that we employ in our experiments, and then I'll show some of these optical experiments for the Newtonian case, the non-Newtonian case, and then I'll show you these interesting phenomena that were found, that's the clustering of the solid phase. And then I'll go on with the conclusions. So as I told you, the experiment that we want to do are optical experiment like PIV and PTV. For this kind of experiment, you might know you need to match the optical properties of the liquids and the solids you use. The solid we chose was PMMA spheres. And so as liquid, we employed, first of all, a solvent, which was made of glycerin and water, to which we could add zinc chloride to change the refractive index of this liquid. Then to this solvent, we could add a certain amount of polymer, of course, changing the rheology of this liquid. And we added the xanthan and PAA. So just to recap, as Tom was saying before, when you add xanthan to a higher concentration, you get both the shear thinning behavior together with the viscoelastic behavior, as you can see from the viscosity against shear rate, the graph, and also the presence of first normal stress difference here. When you add the PAA, you obtain the so-called Boger fluid, so a fluid that has a constant viscosity but still shows viscoelasticity, as shown in one graph. Here I'll jump to the results. In this graph here, report the velocity field of the liquid phase together with the velocity field of the solids. As you can see, this is the typical flow field created by an impeller like this, which is a radial impeller. But the thing that you can notice is that the solids are moving together with the flow, with the liquids, and they're actually moving at the same velocity. We calculated the slip velocity, which is the velocity, the difference between the solids and the liquid, and we found it to be really small compared to the liquid velocity. This means that, as expected, the particle follow the streamlines. I say as expected because if you calculate the Stokes number of this particle, which is an adimensional number that can be used in these cases, it is really small. So we expect particle to quickly relax to the velocity of the background fluid as they do. In terms of concentration, here we report the concentration map of the solids. They reach a certain depth into the tank because in this particular experiment, they are not neutrally buoyant, but they are more or less homogeneously dispersed in this part of the tank. When we increase the Reynolds number, nothing important happens apart from the fact that mixing happens faster, everything is faster, and some of the particles do reach the bottom of the tank. Now, as I was saying, this is pretty expected, not extremely interesting. This interesting part starts when we go to the non-Newtonian case. As you can see from the concentration maps here, Now the solids are not homogeneously dispersed into the tank, but they are clustered in these positions here. In this graph, we report the vorticity map of the liquid, of the background liquid, and you can see that the particles are actually clustering at the center of the vortical structures created by the impeller. Now, if we do change the Reynolds number, so we increase the impeller speed, we do have a change on the concentration map. This is because we actually changed the background flow field. From a 3-vortex structure, we pass to a 2-vortices structure. And so we accordingly see a change on the concentration map. Now, we try to understand what was happening also in a dynamic fashion. And so we have experiments like this that we call time-resolved experiment. For somehow this video should start. Yeah.
That's fine, yeah.
Okay, so yeah, I'll continue from where Giovanni left it. So he basically was trying to show you the video that showed that the particles in the end cluster at the location. So this is the concentrations inside the vessel, and what we can see is that the particles cluster in the regions where we have the vortices and the vortex centers. Okay, this is having a plane view, looking at the front of the vessel, while now this one is a view from the top, which it will help us to understand what exactly happens in the vessel in the next slide. What we can see is that there is actually this very strong motion happening, radial circumferential motion that is happening in the vessel. Giovanni, do you want to continue? I can don't share. I'll work with the slides.
Okay. Yeah, I'm sorry. Okay, that's
okay.
Fine.
Yeah, so, because I think the video froze it. And
yes.
yeah. Mm-hmm.
Yeah. Okay. So in this slide here, we just show the additional measures that we did to actually understand what was the exact flow field created by this impeller. Because I don't know if Professor showed you, we think that this migration is happening because of the viscoelastic induced migration that we know happens because when 2 criteria are met. The first one is that the background fluid is non-Newtonian, viscoelastic in particular. And the second thing is that we need to have gradients of shear rate present into our vessel. And that's why we perform these additional measures on the vertical plane and the horizontal plane. So if you go to the next slide, we actually understood what's the nature of this flow. This flow is basically mainly a rotation around the z-axis, so a vertical motion created by the rotation of the impeller, and superimposed to this main flow, there is a secondary flow, vertical in the z-axis.
We've lost your sound again.
Okay, maybe maybe I should continue with the.
Yeah, that would be great, thanks.
Yeah, okay. So yeah, basically the idea is that there are 2 main motions happening in the vessel, and that's why we needed to have our measurements both on a vertical plane and on a horizontal one. And this actually, and there is this motion happening on this horizontal plane, but what we think that causes the migration, the movement of the particles to the core of the vortices, is actually this motion here. And what happens is that, and this is a phenomenon that has been documented in the literature for flows in pipes, what happens is that the particles, as they are caught in this circular motion, they experience different normal stresses from the surrounding fluid, which they depend on the also the shear rate gradient. And that's why the forces in the end, the average of these forces, pushes the particles to the middle of the core, to the middle of the vortex. And what we also found is that this migration depends very much on the elasticity of the background fluid. So we did observe this migration for just the xanthan gum solutions, which are viscoelastic fluids, but also shear thinning, but with the Boker fluids as well, which means that actually this migration is a result of elasticity rather than a result of the shear thinness of the solution. And what you can see here is that, and what we observed is that actually the difference in elasticity between the two solutions, Bocher fluid solutions we used, B1 and B2, resulted in actually different migration times that we can see here. So what we have plotted here is this dimensionless migration time for the 100 PAA solution and 200 PAA solution. And you can see that the more viscoelastic, the fluids with the higher elasticity or the higher normal stress differences actually results in a faster migration. The dimensionless migration time is much lower than the solution of 100 ppm of polymer. So we are now trying to explore these results further, and we are working with the numerical simulations of this type of flow. And we are trying to look a little bit more on the fundamentals, but also to understand what happens in stirred vessels. We want to be able, by doing that, we want to be able to actually decouple the viscoelastic effects from any other mechanisms that might be causing this particle migration. And of course, we need to relate these migration characteristics to the rheology of the suspending fluid. And in parallel, so I should say that this work has just been accepted for publication in the Physical Review Fluids. And in parallel, we are also continuing our work on moving from batch to continuous processing, which was one of the objectives we had within Coral. And again, there we have to explore how the viscoelastic effects of the fluids affect the flow and the mixing in online static mixtures like this one. So that was the presentation from all of us. So I think I need to stop sharing. Is that right?
It's okay. So we can override. That's okay. So
okay.
Do you want to just start your video again, if that's okay? Thank you. So, and then we've just got, thank you. Okay, brilliant. Thank you very much for that presentation. Very interesting work to hear all about that. So we've just got one question from the chat. So, which says, it's amazing to see these complex systems that you're able to get with CDF simulation with the complex steered vessels as well. So what factors are not considered? And they wondered whether particle breakup was considered.
So the particle?
So was particle breakup considered? So what factors
okay.
are not considered? Yeah.
No, not in this work. So in this, the results that Giovanni showed in particular, we had spherical particles, and so aggregation or these effects were not considered. We have been looking at these aggregation effects in the rheological measurements, and that I mentioned briefly in the beginning. And actually, there we use different types of techniques. It's called Rheo-PIV, where we can actually observe, obtain the rheology of these complex mixtures together with the microstructure information, the microstructure, whether the particles aggregate, they form any aggregate or breakages within the rheological cell. But not in this one, but yeah, it depends also on the types of particles that are included in the vessel.
Okay, thank you very much. Hopefully, Simon, that answered your question. In the interest of time and to reflect that there's no other questions in the chat, I would like to thank you for your presentation and for concluding our session today. Thank you very much. So also thank you for the reminder it was International Women in Engineering Day. So and I can't believe I actually forgot. So it was it's been on my mind for a few weeks, and yes, thank you very much for the reminder. So one of the comments in the chat was it was great to see that we have at least one female presenter. So yeah, well, we do recognise it's something that the Royal Society of Chemistry and the Formulation Science and Technology Group do look at in terms of our diversity of speakers and on panels and things like that. So it was just so with this particular call, obviously we're made up of people that were the PIs of the grants. So it's wonderful that we've got. We've got you here. So and yeah, so that's thank you, Simon, for sharing that now. So, and yes, and I think, you know, so the researchers that we have working on the grants, I think, you know, it's clear from the posters and things like that, that we do have a very diverse mix of men and women, and from all different backgrounds as well, which is fantastic. So I'm going to now hand over to Simon and Phil just to conclude the day, to thank everyone, the poster presenters, for their work in terms of recording, pre-recording the posters and sending those in advance, and also for the speakers that have joined us today, and thank you very much to the delegates. So Simon, Phil, I'll just hand over to you.